Hello everyone. In this video I'm just going to run through some Lewis dot structures. I will define the shapes and the bond angles for these structures. This is actually the worksheet that is due on November 3rd or something like that. Anyhow, so some of these you've seen before and others you haven't. For the ones that we've seen a couple of times now, I'm just going to skip over those. But let's just talk through this first one. Okay, so here's phosphorus triiodide. Okay, phosphorus is in the 5A column, so it's got 5 valence electrons, and iodine in the 7A column, so it's got 7 valence electrons. All right, so the Lewis dot structure is going to look like this. We have a lone pair of electrons here, which will influence the shape of this. The lone pair with the phosphorus is going to push these iodine atoms down. Okay, that's valence shell repulsion that we're seeing there. Okay, so the ball and stick model would look something like this, attempting to draw this in 3 dimensions with the lone pair there. Remember, the lone pair actually takes up space, so the shape is going to be trigonal pyramidal. All right, so trigonal pyramidal, and the bond angles there will be less than 109.5. If it was a simple tetrahedral structure, the bond angles would be exactly 109.5. But since the lone pair electrons here actually take up more space than the atoms do, they're going to push down on these iodine atoms more. So, in fact, they get squeezed together beyond 109.5, so the bond angle is less than 109.5. All right, now, we've already done nitrogen in class a couple of times. We've done water a couple of times already. Here's arsenic tribromide. Okay, so we could do this one. Arsenic is in the same family as nitrogen, so it's going to have 5 valence electrons. All right, so let's write this out. Arsenic has 5 valence electrons. Bromine each has 7, so 7 times 3 is 21. So that's going to be a total of 26 valence electrons. Arsenic would be in the middle. Okay, bromines are going to be around the arsenic, Br, Br, Br. All right, I used 246 electrons to bond the bromine, so that leaves me with 20 left over. If I distribute that 20, that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. We have a lone pair around the arsenic, so in fact we're going to see a trigonal pyramidal structure. And again, the bond angle is going to be less than 109.5. Okay? So very much like what nitrogen would do or phosphorus would do, arsenic is in the same family. Okay? Silicon tetrachloride. All right. You may have figured out by now that since silicon and carbon are in the same family, they are going to act very much like each other. I'm not going to count all the valence electrons and everything. I will just tell you that this structure will come out to look like this. Okay. All right. This is going to be a tetrahedral structure, and the bond angle is 109.5. Let's call that trigonal pyramidal. Okay. All right, moving on to the next page then. Here we have hydrogen chloride. So we're going to have hydrogen bonded to chlorine, and this would be the structure. This, of course, is going to be a linear structure with a bond angle of 180 degrees. Linear, 180 degrees. Okay? Okay, so let's not name this one, but there's fluorine connected to a cyanide group. Okay, you don't have to know that. Please don't worry if you're like, wait, what did you just say? Let's just put these together. First, I'll count the valence electrons. So that's 7 for fluorine, 4 for carbon, 5 for nitrogen. Okay, that's 16 valence electrons. So I'll tell you what, I do know that there's going to be a triple bond here because I know that this is a cyanide group. You do not have to know that, but you could try this any way that you'd like. I think you're going to find that you need a triple bond there to make the octets. So anyway, let's see what I've used here. I used 2, 4, 6, 8 electrons for the bonding. So let's subtract that 8 from 16, and we're left with 8 left over. Okay, counting out the leftover electrons. 1, 2, 3, 4, 5, 6. That's going to be 8 around fluorine. We already have 8 around carbon. And these last 2 electrons will be with the nitrogen, which gives us an octet around nitrogen. So again, this is going to be a linear shape, and the bond angle is 180 degrees. All right, let's try the next one then. Okay. Okay, I put a skeleton structure together there with a double bond. I believe that there's a double bond there. Let's just see if I'm right. So I used 2, 4, 6 electrons in the bonding. So I'll take 6 away from my 12. I'm left with 6 left over. All right, I'm going to need 2 pair around the oxygen. That gives 8 for oxygen, and then 2 more around nitrogen, and that gives 8 around nitrogen. So this is our structure. Now, what about the shape of this? This is going to be kind of interesting because we have this lone pair of electrons. And this lone pair of electrons is going to push down on these 2 surrounding atoms. So in fact, now if I drew a ball and stick model of this, that would be nitrogen. This would be hydrogen. This would be the oxygen. I'll put a double bond there. And we have that lone pair there. Okay. Now, if this was a trigonal planar shape, then these bond angles would be 120 all the way around. But we've got a lone pair of electrons there that is kind of acting as if it were an atom, or a covalent bond, but it's actually bigger. So I'm going to draw that cloud even bigger. It's really pushing down on these guys. So in fact, this bond angle is going to be a little bit less than 120. I'll say less than 120 degrees. Okay. I got to tell you honestly, if you just told me that that was 120 degrees, I'd be like, okay, that's fine. I think that's fine. All right, what else? Well, this next one, arsenic nitride. Again, arsenic and nitrogen, they belong to the same group. I believe that we are going to see a triple bond here, and this would be a linear structure, 180 degrees. You can try that out for yourself if you don't believe me. All right, now here's one, and this is a little bit, I would say, just a little bit beyond where we are in this class, and that's okay. Just bear with me as I do this. I'm not going to ask you to do this on a test, but we're going to stick with the way that this formula is written. We're going to put nitrogen in the middle, okay? And we're going to put, now this is called a methyl group. You don't have to worry about that. I'm just going to say that. Don't worry about it. I'm going to put a hydrogen here. I'm going to put a hydrogen there, okay? And if you don't like that, here, I'll change this and put it in a form that's more familiar to you. Hold on. All right, so this is in a form that's a little bit more familiar to you. I put it in blue just to kind of show you that we're going to just treat that CH3 as its own thing, okay? If we were doing organic chemistry, you would understand what I'm saying, but you don't have to worry about it. Really, when it comes down to it, this is going to be the structure. And I could redraw this in a ball and stick. I'm just going to do it this way. All right, here's my ball and stick model. I'm not going to use nitrogen. Back up. All right, here's nitrogen. Okay, let's call this the methyl group, the CH3 group. I'll just color it in so that it's there. That's the CH3 group. And then I've got hydrogen and another hydrogen. Again, I really think that this structure is beyond where we are right now in this class, and don't worry about it. But if I was looking at this structure, then trigonal pyramidal. Okay. Again, this thing right here, I'm just saying that is the CH3. And I think that's a little bit more familiar to you. And please don't lose any sleep over this one, okay? But hopefully you can see why that would be trigonal pyramidal, really focusing in on those lone pair electrons. Okay, and I believe that does it. So I hope that was helpful to you. If there's anything you need help with, please don't hesitate to contact me. All right, thank you.